Good to see all of you here. We're excited to take you into the workshop over the next couple of days. We'll start off with just a few logistics, kind of get ourselves squared away, and then we'll get rolling. So here we are. Here's the course that you signed up for. We'll be talking about two key techniques for quantifying the robustness of causal inferences. There'll be something called the robustness of inference to replacement RIR and impact threshold for confounding variable ITCV. We'll learn about all those as we go along. There will be a brief opportunity to talk about some other techniques tomorrow mostly, and it'll be fairly brief. This is kind of a reduced form course. So we'll be mostly focusing on these techniques and also as they relate to others. We will be asking, what would it take to change your inference? And we'll be using this, our Shiny app some. We'll be using a website, a standalone website, and we'll get the hang of this, but I just thought I would show it to you right now. And there is a QR code for it. You can do it on your phone, on your computer. We'll have plenty of chances to experiment with that. And it also does generate R and Stata code for you to move forward out of the app as you get into more sophisticated applications. But I just thought I'd show you where we're going. And then to hit you quickly with substance, we're going to take a look at two examples of studies that we might apply a sensitivity analysis to. This is almost the end point. One is a study by Raj Chetty and Matthew Jackson. That's an economist and a sociologist on the economic connectedness and upward mobility. Somehow, Raj Chetty's very, very entrepreneurial. Somehow Raj and Matthew Jackson got their hands on Facebook data that most of the public would not be able to access. It's at the zip code level, but they've got they got this Facebook data, and this was an article that came out about a year and a half ago in Nature. And what they found was that there was something about economic connectedness and upward mobility, and in particular, the share of high SES friends among individuals with low SES, which they term economic connectedness, is among the strongest predictors of upward income mobility identified to date. Wow, that's pretty striking. That's about how you move up. There's all kinds of sociological research, economic research, how your parents' socioeconomic status has a lot to do with what yours will be, although there is some mobility upward and downward. And so this was looking at in terms of Facebook, and these are Facebook friends. And we know you don't necessarily see everybody that on Facebook that you're friends with, but it's a general marker. Okay, so if we look at their table, a key table for them is this one on the right, and they are predicting upward mobility. Did you move up in your income level? And the key predictor here is this economic connectedness, which has a coefficient of 0.548 and standard error of 0.038. The metric is a little tough to track on this one because it is at the zip code level. These are some averages and that sort of thing. You could break down the study if you wanted to. But let's just take a look and see what it would take to change our minds, because there could be all sorts of things that could nullify your inference about this finding, right? Oh, geographic location, gender, race, all kinds of things. When you were born, right? Which cohort you're in. So yes, those things could exist, but what would it take to change our minds? Well, let's figure that out. So we are going to take this coefficient of 0.548 and enter it into our Shiny app there, and the standard error of 0.038 with a sample size of about 24,000 and one covariate. So all I did was I took a table, a published table, and I extracted key pieces of information from that, and you'll learn how to do this. We'll have time to do this using the app, but I just thought I'd show you now how it's done. And then we click run, and we find out that to nullify an inference, about 86% of the estimate would have to be due to bias. That's using statistical significance as a threshold for inference, which we can talk about. That would mean a way to interpret that is to nullify the inference, about 20,000 plus observations would have to be replaced with cases for which the effect is zero. So yes, there could be sources of bias. Does the bias would the bias account for 86% of the estimated effect? Or, or alternatively, would we say that the bias is accounting for about 20,000 plus of the cases? So what's happened here with this simple example is we have not validated the inference. We don't know for sure one way or the other, but we've changed the way we talk about it. And that's what sensitivity analysis is all about. It's all about the conversation that we're going to have. And now instead of saying it could be this, it could be that, we know what the properties of this or that would have to be to change our minds. Let's do a second example. This is from Michael Gottfried. I have an education background. Matt referred to that. This is a fairly well-known researcher and a very strong education journal looking at the effect, the relationship between student attendance and achievement in urban elementary and middle schools. They used instrumental variables, which I'll maybe comment on a little at some point, but we'll kind of slide past that for right now. And I'll note that this was published in 2010, but I think it picked up in its citations during the pandemic because kids weren't going to school. And part of the findings here are going to be when kids don't go to school, they don't learn as much. Now, school initiated absences versus individual absences are two different things, but during COVID, it was sort of difficult to figure out. Kids were absent a lot for their own reasons. They were sick, their families had stress, etc. So let's see how this one plays out. So may have an estimated effect of 0.014. That is for each day absent. This is the change in achievement on a standardized test, a value-added measure. That is, they controlled for prior achievement, which we'll talk about later on. But it's from a fairly sophisticated model with lots of covariates. And the estimated effect is 0.014. The standard error is 0.001. There's about 18,000, almost 19,000 observations. And if you do a little bit of detective work, you'd find out that depending on how you wanted to carve it up, there are about 237 covariates that were controlled for. So we can crank up our app again, put in all those numbers, click run, and find out that in this case, to nullify the inference, about 86% of the estimated effect would have to be due to bias. And you'd have to replace about 16,000 observations to change the inference. We also showed the ITCV, the impact threshold for the confounding variable here, and we find out that an omitted variable would have to be correlated at almost 0.3 with the predictor of interest absenteeism and with the outcome, change in achievement, to change the inference. So yes, there could be an omitted variable. How strong would those correlations have to be? About 0.3. We are going to unpack these statements. There's lots going on. We'll talk about benchmarking. We'll talk about different types of models. But just to give you the feel for where this is all going, at some level, if you could process and anticipate it better than I ever could what all these statements, then we'd be done. But there's a lot to unpack. So good. All right. I'll just pause here and note that if you have questions as we go along, we've got about 10, 12 people, something like that, online. That's relatively manageable. So you could pop something into the chat. If you put it into chat, it's a little tough for me to see it while I'm going. And we can try. I'll have various pauses as we go. And if you hold your questions for those out loud questions for those pauses, you'll get a chance to ask them. And right now I'll take a pause and see if we're just on track with everyone following with the PowerPoint and what I just did. All right, good. I will continue rolling along. So we'll do just a little bit of setting the context, setting the ground rules. The motivation for what we're doing is that inferences are uncertain. It's causal inference, not causal determinism. So what we're going to ask is, do you have enough information to make a decision? So instead of saying you didn't control for something, we're going to say, what would that something have to be to change your mind? And this, we think, promotes scientific discourse because it's not just there could be, it's what would that thing have to be quantitatively. Um, and we think this informs pragmatic policy. So that's kind of the overall motivation for what we're doing. We'll say more about that as we go along. The goals for the course are to get you to understand, lay out general sensitivity analysis. And for those who filled out the Qualtrics poll, thank you. And it seems like folks would, we're starting with not much, there hasn't been much exposure to these techniques. So we're going to do that. And then we're going to walk you through the robustness of inference to replacement. That's how much would the data have to change your mind. We'll do conceptualization, application, interpretation, and extension to logistic regression. And I did note that in the Qualtrics poll, there are a few people who wanted to see that. And then we'll talk about the impact threshold for a confounding variable. Then again, we'll walk through kind of the same sequence, including maybe some applications in your own context to multi-level models, diff and diff, regression discontinuity designs, that sort of thing. And then tomorrow afternoon, the idea would be for you to, we're going to talk through your particular interests, the particular models, how these techniques might be applied, maybe to a paper that you've seen published that you want to think about, or some output you cranked out yesterday. And the idea is to build a conversation also among all of you. So again, with a little promo for the join the Slack, if you like. What you're going to need. We are assuming when we generate our materials here and when I present, your statistical knowledge includes you understand what an estimated effect is, a standard error, a p-value, hypothesis testing in a linear model. And the examples that I just walked us through from Gottfried and from Chetty, we're drawing on those ideas. And there just isn't time in this course to introduce and establish a baseline understanding of those things. So I'm going to say at times, standard error, and hope that you would know that that's the the standard deviation of the estimated effects in some sort of sampling distribution, and a p-value that you would understand what that is, etc. Your motivation is perhaps even more important. I'm assuming that you want to inform policy and practice, that you're not necessarily looking for mathematical proof of something. There's plenty of math in the slides we're going to do. And at times we try and do a lot of math in our work, basically, so you wouldn't have to, so that you can apply something fairly intuitive with a little bit of math behind it. If you have examples of where you'd like to apply sensitivity analysis, that'd be great. Even if they're not specific, if you can think, oh, that review that I wrote or the reviewer I wanted to respond to 6 months ago really could have used this. Good. That's where we want you to be. And that you're ready to have a conversation about inferences, which sounds like maybe that's obvious. But I will say that I'll anticipate something that's going to come up later. It comes up every time. Someone's going to say, what's a threshold for good enough sensitivity? I gave you a percent, 85%. Is that enough or not? Is 40% enough or not? As soon as I give someone a threshold, that's the day the conversation ends, because they say, oh, I exceeded the threshold. Now I don't have to talk about it. We're done. And our point is, no, we're not. We're going to resist giving absolute thresholds for sensitivity analysis because we want to have the conversation. So there won't be a final answer here. It's you're trying to get to talk with people about the inferences that you're making. Range of levels of material. Some of this, I think, is going to be very basic. It won't even draw on p-values or standard errors directly. And now the robustness of inference replacement and fragility are pretty mechanical, very visual procedures. So good. When we get into the impact threshold for the confounding variable, that's a little bit more advanced technically, a little bit more math on the slides. When we get into mediation or event history, if we get there, the same thing, a little bit more math there. But again, we've tried to do a lot of it for you so you can use something with a fair amount of intuition. And I'll be covering the range. So at times, I'm just going to do basic building blocks to get us all on the same page. And if you already know what something is, hang in there with me. I'll move on to there'll be chances for you to explore more deeply. And then we'll all know at least we have the same notation in what we're talking about. And sometimes I'll get into more advanced techniques or explanations. And if that is just not where you're at, that's fine. Tune out, answer an email, whatever. And then I'll be coming back to it. And you'll get plenty out of this if you have sort of the basics. Sort of a high level overview of what we're going to cover is we'll start today with the robustness of inference to replacement, and that's what we'll be spending this morning on. I'm in the Eastern time zone, so morning here, and we'll talk about an example, kindergarten retention and achievement. We'll learn about the software, and we'll got a little discussion exercise. In the afternoon, we'll turn to external validity, and we'll get an extension to logistic regression. Tomorrow, we will turn to we'll do a little review, and then we'll turn to the impact threshold for the confounding variable, this alternative framework that's based on correlations. When we do that, if there's time, we'll be able to relate either of the techniques to some other techniques that are out there. We're certainly writing about that these days. We'll see how our timing goes. In the afternoon, what I'm hoping we'll do is put a bunch of special topics out there, event history, mediation, whatever it happens to be, diff and diff. And you all will choose one or two that you really want to focus on, and we'll try to support that. We'll kind of run around, and I might get a little bit of help tomorrow afternoon. And then, then you'll be off and running, because nothing like authentic learning, applying it to something you really care about to really make you dig in. And then we'll do a little conclusion. That'll be a little 15-minute wrap up. So that's kind of the plan. And we're ready to go into the robustness of inference to replacement. So this is what we'll be working through. We'll get into the conceptualization of robustness of inference to replacement, then we'll work our way through this kindergarten retention example. We'll talk about what to publish and interpretation. We'll talk about benchmarks, software. We'll do an exercise. Like I said, I don't know if we'll have time to do that group discussion. We'll see. And then we'll be, after lunch, we'll be getting into these other things. And again, these are all now hyperlinked. And this is a purple slide with the hyperlink, so you can use that to navigate. Okay, get us going. So we are going to think about policy, public, and pragmatic sociologies. It starts with an inference. X causes Y. I say one thing causes another. I say being absent from school makes you learn less. Or having friends from higher SES increases your economic mobility, something like that. And with that, in a pragmatic world, there'd be a call for action. Hey, let's get more kids in school. This would have implications for schools being open or not. And that would be sort of policy sociology, as Michael Buravoy would refer to it. When we do that, we encounter the public and probably publics, multiple groups of stakeholders. And what we're doing is we're basically asking for resources to be allocated differently. So in the case of absenteeism in schools, if you really believe that being absent reduces learning, you might allocate resources to have social workers do more to get kids in school, to have schools be more open and available to kids somehow, transportation, all kinds of things that you would really want to put resources into to make sure that kids can get there, make it as easy as possible. So you'd be asking for resources. Well, there are some people who might not agree with that. Whatever resources you wanted, they want the resources used for something else, after school programs or whatever it happens to be. So they might say, well, you cannot prove that X causes Y. And if you cannot prove that X causes Y, then your call to action isn't valid, isn't justified, and we would like the resources back over here. That's very stylized and idealized, but that's roughly how these conversations can go. And I can come up with examples in education all day long. A very recent one is the science of reading, where there's certain psychologists, neuropsychologists who are pushing recently for more phonics-based education. And this has gone back and forth over the last 40 years. and they would say, let's have kids really learn the specifics of phonics. And this debate is playing right out. And folks are saying, well, can you prove that whole language or phonics really works? So instead of saying, can you prove, we're going to say, is there enough evidence to act? So instead of a solid line, if you go back and look, there was a solid line before, we put in a little dashed line here. Is there enough evidence to act? We think that's probably the more relevant question, the pragmatic question. And if there is, it leads to action. And the allocation and the resources might be allocated, but with some discussion and compromise. A very famous example of this, and really the first example of sensitivity analysis that I'm aware of, is the effect of smoking on lung cancer. So in the 1950s and through the 60s, while there were some folks saying smoking causes lung cancer, we should take action in terms of advertising, limitations, et cetera, taxes. And there are some folks who said, you cannot prove that smoking causes lung cancer, and therefore we should not be taking those actions. So this is a very public health example. And in particular, it was Fisher, Sir Ronald Fisher, who developed half the statistical techniques that we use every day, analysis of variance, not developed, but contributed to regression analysis, of course, Bayesian statistics. I mean, Fisher's just dominates a lot of our statistical thinking. Null hypothesis statistical testing is part of his work. So what did Fisher say? Fisher, in this journal called Nature, which is a very prominent journal in the late 50s, said, gee, both characteristics, smoking and lung cancer, might be largely influenced by a common cause, by genotype. Fisher was also a very famous geneticist. And if you read some of his work, this is just one, there was also one in Science, he will have your head spinning. And he was also a pipe smoker. So he had other articles. Well, if you smoke a pipe, it's not as bad as if you're smoking cigarettes. So basically, Fisher is saying there's some omitted variable that hasn't been accounted for, and therefore we should be cautious about the actions that we take. And it's very hard to refute that argument 100% because it's hard to randomly assign people to be smokers or not. You could randomly assign them to some sort of treatment program, but that's going to involve other assumptions. Well, Jerome Cornfield, who comes off as just kind of an aw shucks, I'm just trying to get it right kind of guy. I don't really know if that's his personality, but I've read a little about him. Says we should really be thinking about how much evidence there would have to be to change our inference. And this paper says recent evidence and a discussion of some questions. So it's about a dialogue with the public. That's Cornfield's orientation. And in this paper, they developed a very early version of sensitivity analysis that we'll see here. So the way Cornfield wrote about it was a little awkward. So Rosenbaum picked up on Cornfield in many, many writings. And Rosenbaum summarizes Cornfield this way. They found that an unobserved characteristic would need to be a near perfect predictor of lung cancer, and about 9 times more common among smokers than among non-smokers. While this sensitivity analysis does not rule out the possibility that such a characteristic exists, it does clarify what a scientist must logically be prepared to assert in order to defend such a claim. So this is a relatively intuitive way, or at least it's making it not just, oh, there could be a variable, but what would that variable have to look like? Let's really get down to it, Mr. Fisher. This kind of analysis was compelling. And if you follow into the literature, Cornfield, the paper I just showed you here, and then and other papers that Cornfield and colleagues wrote, influenced policy in the US and Great Britain. And even though you had Fisher arguing, well, you can't prove it, very, very well-known, prominent statistician. So policy moved. And this was part of the key analysis that moved it. we're going to try to improve upon this a little bit because this is an accurate statement, but it's still a little tough to track. It would have to be a near perfect predictor of lung cancer, 9 times more common among smokers. Those are two things I have to hold in my head that are a little tough to track. We think we can sharpen that a little bit, but we're definitely following in the footsteps of cornfield. Okay, so the first way we're going to work here is to think about how much bias there would have to be to nullify an inference. And then we're going to translate that into how much of the data would have to be replaced to nullify an inference. We'll talk about internal and external validity. Internal validity is what percentage of the cases would have to be replaced with counterfactual cases with zero effect to nullify the inference. And for external validity, what percentage of the cases would you have to replace with cases from an unsampled population with zero effect to nullify the inference. These are both going to fall under the general heading of the robustness of inference to replacement. How would your data have to be different to change your mind? We've written several papers on this. The sharpest one, the one that brings a lot of ideas together, is this one. What would it take to change an inference? And that's the more or less the RIR approach. There's a hyperlink to it that would take you to the readings folder that you have access to, so you can read up more on this. There was an earlier paper in 2007, one in 2008, that made the same ideas, but this one's a little bit sharper. Okay, so let's get into it. Let's look at studies A and B. So each of them has an estimated effect. We have some sort of threshold for making an inference. If the estimate exceeds that threshold, we infer there's an effect. If the estimate does not exceed that threshold, we say, well, there's no effect. And then we talk about how much of the estimated effect is above the threshold. So if you look at studies A and B, both studies exceed the threshold. So technically, you'd make the same inference from studies A and B. But if all else being equal, design, measures, sample, et cetera, all else being equal, the estimate from study B and the inference from study B looks more robust. Why? Because more of the estimated effect from study B exceeds the threshold than from study A. It's a very simple idea. Baked into this is that there is some threshold for making an inference. Above that threshold, you make the inference. That threshold could be statistical significance, which we'll work with, but the whole framework applies if you just have a threshold that's in terms of an effect size, or a clinically meaningful effect, or any threshold. The idea of the threshold is linked to the pragmatism. When the evidence exceeds the threshold, that's when you take action. You could have multiple thresholds. We can talk about all that. If the evidence is this strong, I take one action. If the evidence is that strong, I take another. All still works. But there's a point, if you're thinking about evidence-based practice, then there's a point at which the evidence is strong enough to inform practice, to change practice. So I want to get you thinking about that. And some people might say, well, I don't make inferences unless I see a meta-analysis. Okay. And in the meta-analysis, there's still an overall effect size that is still either strong enough or not to make an inference. Or you could say, well, a synthesis. I don't make an inference unless I see 5 studies supporting the action. Okay, let's say there are 4 studies that already support, and we're looking at the 5th. There's a threshold for that 5th study. If it's strong enough, now you've got 5. If it's not, you don't. So I think if you chew on it a little bit, if you're interested in how evidence informs practice, there are implied thresholds in almost everything we do. And that's part of what this slide is bringing about. Now, when we talk about thresholds, we're going to weigh the evidence against the threshold. And there are certain things that might make us ask for more or less evidence. So if there are huge concerns about bias in a study, then we're going to ask for more evidence. Oh, this study had bad measures, all kinds of selection bias into the treatment, whatever. Okay, well, it's still potential that you could potentially still make an inference, but you'd ask for a lot more evidence. On the other hand, if there's a huge return on investment, an example I can give here is early in the pandemic, there was an idea that I think still holds some weight that Pepsid could slightly reduce the effects of COVID. Well, that's a huge return on investment because Pepsid's pretty cheap medicine available over the counter in the US. And so you might say, well, and it doesn't have too many side effects. You might say, well, we'll ask for modest evidence of an effect for something that has such a high return on investment. So we want to be thinking about the design of the study, the return on investment, the impact of the findings when we're thinking about how much evidence we need. We can talk a long time about thresholds and the criteria behind them. There is an extra PowerPoint on this, and we've written a little about that. All right, I am going to skip this slide. We'll come back to it. I'm going to do it graphically. So just to introduce a little bit of notation then, we are going to use delta to represent an effect. Delta hat represents an estimated effect, and delta pound sign we'll use to represent the threshold. So when we want to characterize how much of an estimated effect exceeds the threshold, we'll say, well, we could have delta hat minus delta pound sign. That's the difference between the estimate and the threshold, divided by the estimated effect. And just a touch of algebra would say that's 1 minus the threshold over the estimated effect. So for study A, that would give us 1 minus 4 over 6, or 1/3. 1/3 of the estimated effect in study A exceeds the threshold for making an inference. And for study B, it's 50%, half the estimated effect. Half the estimated effect would have to be due to bias to change the inference. Half the estimated effect is above the threshold. So I'm just kind of introducing the notation of the threshold. If you want to see a little bit of math about how this works out in terms of how we get to this expression, you can go back to slide 30, but I think I've got another slide on it related later on, and so I think graphically you probably get it. All right, a little knowledge check. So I'm going to do this in terms of the poll. Oh, and I see the chat's been lighting up. All right, we'll do the poll, and while we do that, I'll go ahead and check out the chat. This is an anonymous poll. I just want to get a sense for where you're at. So if you go ahead and fill that out, I'd appreciate it. All right, we'll end the poll. Share the results. And you should be able to see these results. And we're on track for the most part there. Yep, we would say we're learning about how much bias there would have to be to change an inference. One person checked C here and said how much bias is accounted for by the covariates. We will use information about bias accounted for by the covariates later on, but right now we do not know. For the analysis I just presented, we do not know how much bias is accounted for by the covariates. We only know how much there would have to be to change your inference. Good. Oh, sorry, little problem with do this. So the answer is B. And do this. And I did look at the chat, and I'll note for David Miller, who wants to talk about sample size and things like that. We will definitely be talking about that. Hang in there with me. It actually won't take too long. Before lunch, we'll get to it. All right, good. Well, I'd say we made some progress because talking about percent bias to nullify an inference is intuitive. It's better. I think it's better than saying, well, that's highly significant or barely significant. Now you can put a very sharp marker on it. What would it take to change your mind? That said, it would also be nice if we had a little bit more of a framework for interpreting. In particular, bias can mean so many things to so many different people that if we can get ourselves thinking a little bit more concretely, there would be value for, say, practitioners, policymakers, researchers, all to be talking in the same language. So that's where we're going to go. So to do that, I'm going to introduce the idea of the counterfactual. Now, some of you might have been exposed to the counterfactual before, but I'm going to use it to set up a little graphic, and that'll set us up for the sensitivity analysis. All right, so the counterfactual. I have a headache. I take an aspirin. The headache goes away. Is it because I took the aspirin? The answer is we'll never know. It's counterfactual for the individual. Because in order to know that taking the aspirin made the headache go away, you would have to see two versions of me. Exactly the same me, exactly the same time, with exactly the same headache, one of which took the aspirin and one of which did not. And then you could compare the two results, the two me's, and know exactly what the effect of the aspirin was. But if you give me the aspirin, then you cannot observe me without the aspirin. And if you don't give me the aspirin, then you cannot observe me with the aspirin. So one of those two outcomes, one of those two potential outcomes, will be counter to fact. And therefore, it's called the counterfactual in the potential outcomes framework of causal inference. You can read a bit about that if you like on this hyperlink. It should take you to Paul Holland's 1986 piece, which picks up on Don Rubin's pieces in the 70s and earlier, sets up this whole framework. It's been used extensively for mediation, for propensity score modeling, mediation analysis, all kinds of things. So this is the basic idea of the counterfactual. Just to get you a little bit more background on it, let's say we've got Julio here, and we want to think about Julio's outcome if he was retained in kindergarten, that is, he was not promoted, or Julio's outcome if he was promoted to first grade. And so we've got Julio, and we would really, to know the effect of being promoted in kindergarten on Julio, we would need to see two Julios, one in which he was retained on the left, and the one on the right in which he was promoted. And then we could compare those two and know the effect of retention for Julio. So the problem of causal inference is that you can't see both those things, and for a single person. Now, what we do often is we say, well, we can't see it for a single person, but we're going to have a whole bunch of people, and we will compare the ones who are promoted with the ones who are retained, the ones on the left with the ones on the right. And let's just say that these two were actually retained and only Julio was actually promoted, or I'm sorry, these two were actually retained and only Julio was actually promoted. Then you can compare the kids who are promoted with the kids who are retained. And then there are all kinds of assumptions baked into that, because you have to hope that when Julio was promoted, he represents what would have happened to all the kids had they been promoted. And you have to hope that the people who were retained represent what would have happened to all the people if they had been retained. And we can achieve that representation in theory through random assignment if people comply perfectly with how they're assigned. But that is what we're doing. We're leveraging information on groups because of the fundamental problem that when we're looking at an individual, we can't do it. We don't have the information we really would like to have. It's fundamentally missing, counter to fact. So we move to groups. And as soon as we do that, we have all kinds of procedures, random assignment or other, and assumptions that get baked in. I'm going to do this slide. It's a little bit more background and context, and then we'll get into a little bit more of the technical work behind it. So back to the pragmatism, if we talk about people who are treated and we want to compare the observed treated group to the unobserved counterfactual group, that's going to be our little delta. Those are the true effects. And below the line are researchers. This is the experience of people. And below the line are researchers. Maybe we were smart and collected baseline data and looked at a treatment assignment and then got some sort of post-test. And then we, the researchers, come up with a counterfactual approximation, because we don't really get to observe the counterfactual. So the point that I'm making with this slide is, as soon as you accept or accept the counterfactual framework, then you realize that researchers enter into the equation with their own biases, their own subjectivity, because researchers are trying to approximate the counterfactual. It's baked in. There's a role for us, but that means when we get our estimated effects from groups, we might not get it right. So we need to talk about it. We had our own approaches that we favor, our own covariates that we chose to control for. So then we're going to compare the threshold versus the evidence, and we're going to have a big conversation, ultimately leading to policy, and in this case, to educators, if you want to go for evidence-based practice. So part of the point I'm making here is there are ways that we're going to teach you to do sensitivity analysis, yes, and we think there are better ways, worse, but there won't be a final word, and because your own subjectivity is baked in. And that's true for quantitative research. My qualitative colleagues are always emphasizing this point, and I wanted to bring it out with this slide. All right, so we've got our idea of the counterfactual, and I'm going to show you in this little toy example how the counterfactual is approximated using groups of people. So you've got this little toy data set here, little spreadsheet, and we have 3 treatment cases here. They're labeled with T's, and YT represents their value on the outcome if they got the treatment. So these 3 cases I have scores of 9, 10, and 11. What does 9, 10, and 11 represent? It's just toy data. It's maybe how good I'm feeling having taken or not an aspirin. And I can feel a level of 9, that's pretty good, or all the way up to an 11, that's great. So whatever you want 9, 10, and 11 to represent. Over here, in these yellow cases, we have cases that were assigned to the control, and this is their outcome under the control condition. And they had scores of 3, 4, and 5. The control here might be having not taken an aspirin. And we can see that then these pink values are the counterfactual cases. You will never get to see these. But let's say, just for hypothetically, that I have some sort of crazy information that no one could actually ever see. But in fact, this person who experienced a 9, having gotten the treatment, would have experienced an 8 if they had gotten the control. And same for this person would have experienced a 9, and this person would have experienced a 10. So now if I could see these, which I never will, but just follow me with the thought experiment. If I could see these, it's clear that the actual treatment effect is 1, because for each of these people, they did 1 point better having gotten the treatment than they would have done otherwise. So the effect is 1, and that's a difference between 10 and the mean of 9 here. That would give me an effect of 1. But what we do with the counterfactuals, we say, well, we don't get to observe these pink values ever. So instead, we use the observed treatment cases, the control cases, to approximate the counterfactual for the treatment if, in fact, instead they'd gotten the control. And when I do that, we see, well, now the mean for these cases is 4 instead of for 10 over here. And the difference is 6. I estimate the treatment effect of 6 when, in fact, it's 1. I overestimated the treatment effect. There is bias in my estimate. Why? Because I used the observed control cases to approximate the counterfactual for the treatment cases. That is how the counterfactual enters into our daily work. If you're doing quantitative analyses, one way or another, we could express it as you're approximating the counterfactual. If you're doing a regression, logistic regression, multi-level model, propensity score, whatever technique you're using, event history, it can typically be boiled down to you're approximating the counterfactual in one way or another. So that's the business we're in. That's the business you're in just by virtue of coming here. I'm assuming that you are in this business of quantitative analysis using the counterfactual. All right. Now we're going to turn that around a little differently to do sensitivity analysis. So now let's say we have the same observed data, but let's just hypothetically assume that the counterfactual data, that there's no treatment effect in the counterfactual data, So if I look at the overall mean between the observed cases, it would be about 7. Right? If I just added these up and added these up and then took the mean, it would be about 7. So in the counterfactual data, we'll say the counterfactual data look like this: 6, 7, 8, and 6, 7, 8 right here. Notice the counterfactual data for those who got the treatment are the same as the counterfactual data for those who got the control. And just, to really get you thinking about it, this 6 represents what this person would have experienced if instead they had gotten the treatment. The person got the control, but we're just hypothetically imagining that if they got the treatment, they would have scored a 6. Well, we see that our estimated effect starts off at 6, the mean of 10 minus the mean of 4 gives us the value of 6. And then we can ask, how many of our data points would we have to replace with counterfactual data for which there's no treatment effect to change our inference? If we replace one case, the mean here is now 9. Treatment effect has gone down to 5. If we replace the second case and use those data then to approximate the counterfactual up here, the new mean up here would be 5, the mean here would be 9, and our difference would be 4. So if we replace 2 out of 6 of the observed yellow cases with counterfactual cases for which there's no treatment effect, our new estimate would be 4 instead of 6. If we're using 4 as a threshold for inference, just sort of arbitrarily defined, we can now say we'd have to replace a third of the cases with cases for which the counterfactual cases for which there's no treatment effect to nullify the inference. That's all assuming a threshold of 4. We can work with any threshold, and the original estimate is 6. And we've replaced a third of the cases. So if you've seen the counterfactual before, you might have, and you might not have seen it quite the way I set it up, but now you probably have not seen this kind of sensitivity analysis use of the counterfactual. And so now we could say the inference would be invalid if you replace 33% or 2 of the cases with counterfactual cases for which there was no treatment effect. And I'll come back to this, and we'll just go to this graphic and say, now it's the same graphic we had before. This study A, a third of the estimate would have to be due to bias to change the inference. But now we have different language for it. We say you'd have to replace 33% of the cases with counterfactual cases with 0 effect to change the inference. So we've made it much more concrete. Rather than just talking purely in terms of bias, we've talked in terms of how the data would have to change your mind. And if you want, you can, I'll just pause and let that sink in for a moment. All right, a little bit of comment on that. If you want to, one way to think about this is that we are going to have a final estimated effect that's based on some mixture of observed cases and counterfactual cases. So in this situation, it's the 9, 7, and 11 versus the 3, 7, and 5. And so we're going to have some sort of final observed effect. And that's in terms of some mixture of observed cases. Oh, and that should be unobserved. There should be a UN there. Sorry about that. Let's see if we can fix that. There should be a little UN. Okay. You'll have to correct that on your slides. So if we then assume that the unobserved effect is 0, that is that these would be the counterfactual cases, assume that's 0, and then set this to a threshold and solve for pi, you would get this expression. You would find out that pi equals 1 minus the threshold value over the estimated effect. And so that's just a way of deriving, if you will, the expression that we've got down here. In the 33% of the cases that would have to come from these unobserved counterfactual cases to change the inference. Yeah. All right. There's some folks chit-chatting about power calculations. We'll be able to talk about that a little bit. One way, and this is related to power calculations, is that it can be sample size dependent, but only through the threshold. And sometimes the sample size will enter into the threshold, sometimes not. Another aspect is that power calculations are typically done a priori prior to a study. Yes, we can talk about minimal detectable effect size afterwards. This analysis is post hoc. It's after you've done the study. What would it have taken to change your mind? So it involves some of the same elements, and we'll see that as we go along, but it is distinct from power analysis. That said, you might know Jacob Cohen over my right shoulder here, which is not an accident. I rely heavily on Cohen's work in a lot of what I do. And Cohen was, of course, developed a lot of the ideas about power analysis. Okay, this is a good chance to have a little break and reflection. These should be hyperlinked, these little slides here, so you could use this slide 43 to go back, to navigate back to other slides. And just review a little bit. Where have we been? Pragmatism implies thresholds. How much does an estimate effect exceed a threshold? And then we got to bias to nullify the inference. And we did that in terms of counterfactual cases. You can think about which part is most confusing to you. Is there more than one interpretation? And then in breakout rooms, you can discuss with members of the breakout room. All right. And if I say your name wrong, I apologize. Ofer? It looks like.
Yes.
Yes, go ahead. You have a question.
Yeah, thank you. I have a very basic question. I was just wondering if you could very clearly explain what do you understand under the term sensitivity analysis? Is it the same as power calculation? Is it different? How is it different? What does it mean actually?
Yeah, okay.
Thank you.
All right. So I'll give a two-part answer. The first part, to differentiate it from power analysis tells you the sample size you would need to detect an effect. That's basically, so it's you're solving for sample size. Sensitivity analysis tells you the conditions of omitted data or variables necessarily to change your inference. So you're answering different questions. It comes from some of the same formal expressions, but in its most basic form, you're solving for different things. So that's, and I will have more to say about that when we see the thresholds we define for inference, but that's the first answer that I'll give. And the second thing I'll say is that there is also a flavor of sensitivity analysis where people talk about how sensitive an inference is to observed changes in the model, or covariates or subsamples. Those things are all great. You should do them. The techniques that I'm presenting here are going to be all after you've done the best you can and explored all your different models with your covariates and subsets of data. After you've done that, we're going to take you into the hypothetical worlds that would change your mind. So just differentiating what you could call what I just described, quantifying the robustness of an inference versus sensitivity analysis, which is using observed features. I used to have a slide on that, but it got people confused, so I don't do it anymore. All right, Fulvio, if I say your name right.
Thank you. This approach is based on the idea that there is a threshold that we know, and then but often in empirical studies, we do not know this threshold, so we want to estimate the size of a given effect. So can you reflect a bit upon that? How important it is that we have an ex ante idea of the size of effects that we can use as a threshold?
Yeah, that's a good question. It's a deep question. the techniques that I'm presenting here can all be extended, and in some of our work we do, to the fact that you might not have a single threshold, that you're just interested in the estimate, and the conditions that would change the estimate. And other sensitivity techniques, such as those by the Sinelli and Hazlitt, the robustness value, and Tyler Vanderveel's work, E-value, they typically will present more in terms of just how would conditions change an estimate. And there can be sort of a continuous range of conditions and a continuous set of estimates. So, and those are all technically good, and we can link up with those things. Our worldview is that there are implied thresholds, that even, and sometimes we're not very good at making them explicit. But if one of my opening comments was, we assume that you're trying to change people's behavior in policy or practice. And if so, then it's hard, then probably you're going to say at some point, there's enough evidence here to get us to do something different. And as soon as you say that, we say there's an implied threshold. And if you want to follow up, you can. And then I would also say in the academic world, if you've tried to publish a study that has a p-value of 0.3, and you were not trying to publish a null finding, but you're trying to publish and say there's an effect here and the p-value is 0.3. In most social science, that'd be very difficult to publish. So there's an implied threshold of a p-value of typically 0.05, sometimes 0.10. And I know we should be talking about effect size, and it shouldn't just be p-values, and we'll be able to comment on that. We see gray area around the p-values, which is what this work is all about. So if you have a p-value of 0.049, you don't wave a flag and say, I got it. And if you have a p-value of 0.051, you don't say, oh, nothing here. You're in a gray area. So we want to have that conversation, but there is an implied threshold of 0.05 that's very difficult to get around. And I'll just say one more thing about that, and then I'll get to David. People say, well, Fisher just came up with the 0.05 as sort of arbitrary, but you can think of 0.05 this way. My brother is going to make a bet with me. He's got a coin, and I call heads, and he pulls a coin out of his pocket and he flips it and it comes up tails. Well, I lost. I owe him $1. He does it again, it comes up tails. I lost again. I owe him another $1. He does it again, it comes up tails again. 3 times this coin's come up tails. I owe him $1. I'm starting to get suspicious, right? He does it again, it comes up tails. 4 times in a row, the coin comes up tails. I'm going to grab that coin from my brother and say, I want to see that coin. I think it's got 2 tails. Well, 4 times in a row for a p-value, for a 50-50 shot is going to get you pretty close to 0.05 p-value. So it's not completely crazy. I mean, and that's sort of an intuition. You would accept losing a 50-50 bet once or twice. 3 times you're getting a little worried. 4 times you think there's something wrong. 5 times you really think this is the strangest coin in the world. So so that takes us a little bit into the 0.05, but we will have much more to say about p-values as we go along. And David Miller has a question.
Yeah, thanks. Just in terms of a threshold, I know we haven't recovered odds ratios or logistic regression yet, but might it be something like it would be, the threshold would entirely be a policy decision, but something like an odds ratio for an exposure to a chemical in cancer, if it's bigger than 2, basically, that might be a threshold. You start to look more deeply in it. If it's bigger than 3, you take action. Is that like an example of where one would?
Yeah, absolutely. Absolutely. Those are great examples. And there are slides where you'd be able to explore that in terms of odds ratios. And you could also throw in another threshold, is it statistically significant, which is actually kind of tricky for logistic regression or related techniques. And you'll see why when you start replacing data, the standard error changes. But absolutely, you could have a threshold, just you think 2 odds ratio is good enough to take one action and 3 is another, and that's the world we want to plug into.